好的，同学，那我们就开始上课哈。So we are starting this session. So last time we have finished the previous chapters. Now we go to uh, detection chapter 2. So just for the convenience of your reading, this is the Stephen Case textbook, volume 2, detection theory, and it's chapter 2. So we are at the beginning of chapter 2. That is uh, page 20. So if you want to refer to the textbook, in fact, I would recommend you to take notes and also follow the textbook to uh, to watch this session so that you follow the equations and the statements, and also if there's any additions in the explanation, you will be able to put it in your notes also. Okay, so at the chapter two, uh, it's a summary of important PDFs. So when we are dealing with a lot of engineering problems, particularly signal processing and communications, we have a lot of uncertainties, and those uncertainties are fundamentally described by the probability density function and also the random variables. So, um, in this chapter, we are going to summarize the PDF. Okay, so let's continue. So evaluation, sorry. Uh, Evaluation of the performance of a detector depends on the ability to determine the probability density function of the data samples, either analytically or numerically. So sometimes when this is not possible, we also resort to Monte Carlo computer simulations. So uh, familiarity with the common probability density function and their properties is essential to the performance evaluation. And in fact, besides that, besides performance evaluation, it also gives us properties, descriptions of the property, and it helps in our design, of course. Okay, so uh, a fundamental property and density function properties. Okay, so the first one we'll be talking about is the Gaussian distribution. So the Gaussian probability density function, also referred to as the normal distribution, is a scalar. So scalar meaning that it's a random variable, single random variable, and its distribution is described by this formula. So let's watch carefully. It's a p of x equal to 1 divided by square root of 2 pi, and then sigma square exponent of minus 1 over 2 sigma square, and then x minus mu to the square, and then square bracket, and its domain is from minus infinity to plus infinity, meaning that it's from minus infinity all the way to plus infinity. So it's this way and also this way, infinite in two directions. This is the property of Gaussian. Then, of course, there will be some random variable that is limited in its domain, and those things will be discussed later in the chapter. So in the formula, then mu is the mean, and sigma square is a variance. In other words, if you want to describe a Gaussian distribution, then you need two parameters. One is the mu, the other is the sigma square. So you need two. But we are familiar with this, so there should be no problem with that. But notice that for some distributions, there could be more parameters, more than two. There could be more than two. Okay, so this Gaussian distribution is denoted by mu and sigma square, and we say that x in this notation it means distributed by n mu and then sigma square. So distributed by something. Then if mu is zero, meaning that this is zero. If this is zero, then we can calculate its moments. So the moments will be expected. This is by definition, okay? Moments is defined by this. It's defined. So defined by expected x to the n. So if n is even, then it's 1, 3, 5 all the way to n minus 1 multiplied by sigma n. If n is odd, then it's 0. And this is understandable because it's symmetric, right? If mu is 0, then it's symmetric around 0. It's symmetric around 0. So when you multiply by the odd order, odd exponent of the distribution, then the plus part and minus part cancel out, so it becomes 0. Okay, so now we go to the next one, page 21. So if it's not 0, meaning mu not equal to 0 otherwise. So mu is not 0, then expect of the moments expect of x plus mu to the n is equal to summation of this. Summation n, select, this is to select k out of n. Right? Select n, select k out of n, and then expect xk mu n to the k and do the summation. So yeah, then expect of xk is given by 2.2. So expect xk is by this. So in other words, this is described before here. And then this is the non-zero part, right? Non-zero part, therefore we have this mu and this summation structure. Okay, so that's the moment. And then cumulative distribution function, we call it CDF. CDF for mu equal to 0 and sigma square equal to 1. For which the PDF is termed the standard normal. The standard normal is defined by this. So this is the CDF of standard normal, meaning that it's only good for mu equal to 0 and sigma square equal to 1. Okay, if we have other values for mu and sigma square, then this wouldn't work. Okay, this would not work. And then a more convenient description, which is termed the right tail probability. I'm sorry. Right tail probability. So let me. Okay, so if you have taken notes, then let me delete it and rewrite part of it just for the space consideration. So this is called the right tail probability. Right tail probability. and it's the probability of exceeding a given value defined as Q. Sorry, let me put it. Okay, so that's easier to see here. Right tail probability, and the probability of exceeding a given value. That is defined as Q of x equal to 1 minus phi of x. And phi of x is the CDF, right? It's a CDF. But the right tail probability is called the Q function. It's the Q function. And it's the 1 minus phi x. So that's the right tail part of the probability. And then you see that this is an integration from minus infinity to x, right? And this is Gaussian distribution. So what that means is, if you have a Gaussian, then that thing phi is doing integration from minus infinity up to x, and x is a specific value, so you're integrating this area, right? This area, that's what phi is doing. For Q is doing distribution of Gaussian, of course, and then x to infinity, x to infinity. So he is doing this part. That is the Q function. Q function is doing this part. Phi function is doing this part. Okay, so just a illustration. So the function Q is referred to as a complementary cumulative distribution. Complementary CDF. Okay, and this cannot be evaluated in closed form. Its value is shown in figure later. We will see in next page. And approximation that is useful is also given. So this is the common approximation. Okay, then here is a description of how you use the MATLAB to plot it. And of course, you use Python and a lot of online, even some online websites, they also help you. They also implement those functions, and you can try and maybe you plot some numbers or calculate some values. And as an example, the right tail probability of non-Gaussian. There is also a non-Gaussian. Okay, so the right tail probability of the non-Gaussian is the Gaussian mixture, PDF. Okay, Gaussian mixture. So what do we mean by Gaussian mixture? If we take a look, let's see this part. What is this? This is actually a Gaussian distribution. Right? This is a Gaussian distribution. And then this is again a Gaussian distribution, right? This is what? This is mu. Let's be careful about its parameters. This is the sigma square equal to 1 and mu equal to 0. This is a sigma square equal to 2 and mu equal to 0. So this is a Gaussian, this is a Gaussian. But it's a non-Gaussian. It's a non-Gaussian because it's a mixture. Because you multiply by 1 over 2, right? Half by 1 over 2, meaning you have half of this distribution and half of this distribution. And this distribution is a Gaussian. This is a Gaussian, but it's half and half. Of course, you can say, how about this 0.3, this 0.7? It's good, right? Because you have 30% at this side and 70% at this side. Okay, so in other words, this is a sort of a percentage in this and percentage in that, and therefore it's a mixture. It's a mixture, meaning that you mix one, you mix two or more than two things together. That's mixture. Okay, and then here's a statement about how you can do it in MATLAB or some mathematical softwares. For example, this QIMV is a MATLAB, but I guess a lot of people use different packages, which is also very good. It, MATLAB is one of them, but you use the others, that's fine. Multivariate Gaussian. Now we go to multivariate Gaussian. Multivariate Gaussian PDF is a n by 1. N by 1 meaning that you can visualize something like this. It's you have a couple of things, but then it's n by 1. Okay, so it's a vertical instead of horizontal. It's a common practice though. If you have you have, if you are not familiar with, or you may have curiosity about how come we are using a column vector rather than row vector. So in engineering, normally it's a common practice that we use the column vector as a convention, as a common practice. It's not 100% necessity, because if you use a row vector, the equation changes, but it's still good. But you just have to change the formulation. But for now, we just to be consistent with the common practice, we use the column vector. Okay, so n by 1 column vector x is defined. It's PDF. Okay, this is a PDF defined as 1 divided by 2 pi n by 2 determinant to the 1 by 2, and C, which we will explain later, that's a covariance matrix. And this mu is a mean vector. Sorry. So it's a mean vector. So you have a p of x equal to 1 divided by this. And you can think of it as what? As a like a Gaussian to the degree n, right? You will see something here. You have 2 pi to the 1/2, right? To the 1/2. Now you have 2 pi to the n by 2, right? N divided by 2, meaning it's up to the degree n, something like 1/2 and then to the degree n, so you get n by 2, n divided by 2, and then your determinant, square root of determinant. This is a matrix determinant, and then exponential 1/2 x minus mu. This is common, right? This is common, something like here, except it is a vector version, right? Vector version. So you have a vector version of something, and that is x minus mu. Okay, so this thing turns to a vector version, and then you see here is a square. What does it represent in the vector version? You have a square, then you have a x minus mu transpose multiplied by its original form. Okay, so you have, if you imagine, you have something transpose. Transpose becomes a row vector, and then multiplied by something column vector. Then element-wise multiplication and sum it together, you see a lot of square terms, right? So that's the kind of the fundamental property of a vector version. And vector version is slightly different from a scalar version, except some of the things that change a little bit. So as I say, 2 becomes transpose multiplied by itself. Now you have a sigma square. Sigma square becomes inverse of covariance matrix. It's represented by inverse covariance matrix. So this is something like that. If you put a one by one random vector into this formula, this 2.5 actually reduced back to 2.1. Okay, so let me say it again. If you put a one by one random vector, which is a scalar, this equation 2.5 reduces back to 2.1 because it is a scalar. It is supposed to be a scalar. Okay, so that's a Gaussian. Okay, so let's look at some figures. Here is the right-hand probability of standard normal. Okay, this is a standard normal. You have Q function. Okay, you have a Q function, and this is plotted in a linear scale. Linear scale. This is plotted in log scale. In a log scale. And here is the Q function on a normal probability paper. So this is like a log scale, and this is a log scale. Okay, so let's continue the statement. So continue from this equation where mu is the mean, as I mentioned, C is the covariance matrix, and then it's denoted by mu C. It's assumed that C is a positive definite, and C inverse exists, and the mean vector is defined as this. Notice that this C is in fact a covariance matrix N by N. It's a N by N. So notice the dimension. And let's look the figure again. Just go back a little bit. Write out probability from non-Gaussian PDF. Okay. And the covariance matrix continued from here. Continue from this statement of covariance matrix. Covariance matrix is element-wise definition. Element-wise definition. Element-wise meaning element by element， 就是每一个元素都拿出来定义，叫做 element-wise definition. So Cij is what? Let's take a look. Cij, if I pull the details of C, this is N by N. Now Ij meaning Ij, right? So ith row, jth column. So that element is the so-called Cij. So hopefully you know what the notation is doing. For example, if I say C2, 3, what does it mean? You go from 1, 2, and then 1, 2, 3. That's 2, 3. If I say 5, 7, then what does it mean? 5, 7, that element. Okay, so Cij is the ith element inside the C matrix. And it's taking expectation of xi minus expect of xi. This is what? This is a typical definition for variance. Recall when we are doing a random variable in a scalar version, this is the typical definition for variance, except it is defined by xi and xj because it's ij. It's no longer the diagonal. If it's on the diagonal, then it will be ii, right? It will be ii, for example, 1, 1, 2, 2, 3, 3, 4, 4. But now we are doing 5, 7, or maybe 2, 3. So it will be defined this way. And I can be from 1 to n, j can be from 1 to n. Or in a more compact form as this, you expect x minus expect x expect minus x transpose. Notice that when it comes to vector, I always like to draw to do a visualization of what it looks like. This is a let me see. This is a I'm sorry. Let me make a correction. Make a correction. This is a, as I say, this is a column vector. This is a, it has been taken transpose, so it is a row column. As a result, this is what n by 1. This is 1 by n, and then the outcome is what is n by n, right? N by 1, 1 by n, and the outcome will be n by n. As a result, you get a c, n by n, right? That's n by n. Let's see. So you have x minus this, and then transpose. So this is the second order term, right? Second order term. 所以就是用中文重复一下，就是这是一个column vector，这是一个 row vector。如果你把它乘起来，它就变成一个 n by n，不是一个 one by one 哦，是变成 n by n，所以它就是一个 covariance matrix， 是一个 covariance matrix。那它在 scalar 里面的二次项，在 vector 的版本里面，通常就是一个 column vector 乘以它的 transpose， 它的角色相当于是 scalar 版本的二次项的角色，就是这个二次项这个角色。好，二次项这个角色通常就会变成是这样子的一个乘以 transpose。Okay, so that's a very common practice because you're not only seeing this at this location, you're going to see it everywhere. When there is a second order term, you always see something like a column vector multiplied by a transpose, or a transpose multiplied by a column vector, things like that. Okay, if mu equal to 0, then the arc order joint moments are 0. This is similar to page 20, something like this, right? Something like that. Okay, so even order moments are found as combinations of second order moments. So a useful result for mu equal to 0 will be if you try to calculate the moment, then it's a second order moment, and the multiplier, of course, there are combinations of a second order moments. This is like a four order, right? Fourth order moment, and it's combination of second order moment. So yeah, something like that. So we will end our session, this session here. Please continue and next session from chi-square. So just as a reminder, for the ease of your, for the convenience of your reading, this is at 24, page 24. You can refer to it. Okay.